cool. Now, yep, I am recording. So I wanted to start the recording a little earlier than when class officially starts. So welcome to the recording if you're listening to this later. Um, for those of you who are joining live, let's see, I currently have, it's 8:47 and I've got 1, 2, 3, 4, 5, 6, 7 folks in class right now. Yeah, thanks. And I recognize that not everybody can, or not everybody can every day. I know that there's a lot of changes and things that will be going on in your lives due to. Oh, and I've got somebody. So let's see. Travis has a microphone on. Let's see if I can mute. Yeah, I can mute right there. And then, yeah, okay. So yeah, it's helpful if you mute a microphone. I think Emily as well has a microphone on. I think I can hit the button. There, yeah, I did it. But yeah, helpful to mute your microphone unless you have a question. What was I going to say? Oh yeah, so yeah, just in the recording, this countdown is going on. Again, for me, like starting a little early, the recording, it's this is kind of an intensive process for this poor old computer that I got 6 years ago, to both host the video conference and to record. But having tested it, I know it works. But I just wanted to start the recording a little early and putting this thingy here, just like like I do in class, this thing that shows how the countdown to the start of class. I think that'll be helpful for people who need to watch the video later, so that whether watching the video just by streaming it later or by downloading it, then people know like, oh, there's still 60 seconds. I can just scroll 60 seconds into the video to watch. So I'm just trying to give people their options, and still people are joining us. So, oh, cool. So far everybody who has joined has muted their microphone. So yeah, I know this is strange. Normally this minute or so before class starts, I say something kind of off the wall. Like right now, just beyond this, so this camera, there's a window out there, and there was a squirrel on the fence a little earlier. I don't know where that squirrel went. I don't know where you are, but here in La Crosse, it is a bright, sunshiny day. I think that's a good sign for the day. So, 8 seconds. All right, so here we go. I can start. Let me move this timer over to the other screen so I can see how much time I have. My goal is to not speed up or anything like that. So I do have a separate monitor I'm looking at over to the side. So if you happen to see me through a webcam right now, I'm not looking at it. I have my notes on another screen over here since I can't print things. And the timer is over there. The sort of notes for like who might be raising a hand. If you use that feature, it's over there. I have on a second laptop where I have a camera, so I'm not going to try to make a whole lot of hand gestures, but there are kind of, sometimes it might be helpful, so maybe you can see that on screen, and sometimes the view that you have of me here in this green shirt in a room might get distracting, so I think it's possible for you to hide that or move that to another part of the screen. But just like in class, when I write on the slides like I'm doing right now, you'll see that. I can erase. So kind of the usual things. I actually also, this is a purchase I made kind of a long time ago, and I'll show this in the camera right now. This is a USB microphone. So I actually, I'm trying to keep this close to me. I know from experience last week that if I don't, then people can't hear me. But I also knew from having made videos on this tablet in the past that if I don't have a microphone like this connected, then because the microphone's embedded right on the screen, as I write on the screen, you'll hear too much sort of clicking noise. And it's not the worst thing in the world, but to try to kind of, you'll still probably hear a little bit of it, but this using an external microphone like this helps quite a lot. So there is a warm up here. Welcome back. I know this is strange. I know you didn't sign up for this, but before we get started, I guess I need to say that I'm here for you. I almost had my emotional moment last class, so I think I'm actually kind of through that right now. Um, I guess I'll just say I know you didn't sign up for this. Hang in there. I want you to do the best that you can. I want to try to still make class as normal as possible given the strange circumstances. Just communicate with me if something comes up. I'm going to try to be as flexible as possible. If something's not working for you, please complain. I will. I mean, we might not stick to even exactly this format if it's not going to work, right? I hope it does. I value trying to create as much consistency for you as possible to try to make my expectations as clear as possible. But I hope you'll be forgiving and will be flexible. I will do my best to try to make this work for you. If you've joined now, as I've got 15 people in the online class, great. There's a great opportunity for you to ask questions by joining this in this format. But again, as I said before class officially started, people won't be able to every day. I recognize, due to new arrangements and perhaps being at home, you may have to watch after a kid sibling, all kinds of things that are not usual, or internet connections that are not as reliable. So that's why I'm intentionally recording the videos. I will upload them as soon as I can, but it does take an hour to process on the laptop, and then once I upload it, the server where I'm uploading to, it takes its own half hour or so, I've noticed. So the recordings won't go up right away, but I'll do the best that I can. I instead of uploading the videos to YouTube where you can't download videos, I didn't want that. I wanted to use another thing that we have on campus where people can download the videos. So if people had to temporarily go somewhere where there's a better internet connection to download videos, I wanted that option. I found out Murphy Learning Center does have online tutoring, so please make use of that. The link I just posted in Canvas last night. Again, if you can make it to class live, that's ideal, only because you can ask questions. That's I think what's good about that. But if you can't make it to class live, just download the slides, look through the slides, or watch the videos after. Though I would encourage you to keep pace. It's easy to just say, oh, I'll watch all the videos before the next exam or something. It doesn't happen. That's just too much stuff. So try to do something to keep on a regular schedule of some kind. I would encourage you to take notes still as well. It's easy to say, oh, I don't need to take notes now that everything's recorded. I'll just watch everything again, as a review before the exam. That's a lot of videos to watch before. It doesn't happen, right? So, and then there is a quiz tomorrow. So what I want to do is there's a pretend quiz. I want you to try the pretend quiz. It's not for points, even though it says it's for points online. It's just to try out the format. I tried to pick a sort of typical calculus question from the first half of the semester. Try the pretend quiz just so you see the format. It's open and available all week. And then tomorrow, since it's a quiz day normally, there's a quiz online, and just sometime between midnight and midnight, just sometime during the day on Tuesday, just take the quiz online. It's at any time that's convenient for you. I don't want you to work with anybody else. I'm trusting you on this. I know these are unique times, but I'm giving you an hour to complete it. Not that it takes an hour, not that I want anybody spending an hour. The whole point is it's just like any of our quizzes we've done in class. Think of it like that little half sheet. I can't ask anything much, and I don't want to ask anything that takes up a lot of time. 5-10 minutes is all I want you to take, really, but I'm giving you that hour just so that any kind of technical hiccups you run into, I don't want that to be the thing that causes any stress. Again, if you run into any trouble with taking the online quiz, just ask, just send me an email and we'll figure things out. So I'll pause right now. I just wanted to, before we dig into math, because for me, I am really actually as painful as this format is, I'm excited to do things again and to try to make things normal. But before doing so, are there any kind of format things I can answer for anyone? So I notice everybody, I think, has their microphone muted. So if you've got a question, you've got to unmute your microphone and then ask your question. Nobody else will hear, I think. Well, no, that's not true. Everybody else would hear your question, but not in the recording. So I'll have to repeat the question if you have it. Any format related things that I can help answer right now? Okay. Well, then let's do this. Oh, and I forgot to just mention, if you haven't had a chance to do so, there is a video that the campus put out recently. I didn't know that they were going to make me first in it, but yeah, it's on Instagram. It's on the campus Facebook page as well. It's really awesome to. Oh, okay. I said I wasn't going to get emotional. I already did it last section, but I watched it several times, and I just have to say that I think I echo a lot of the things beyond just what I said. The faculty and staff are really trying our best to look out for you. So if something comes up, just let somebody let somebody that you trust know, and then we'll figure things out. All right, let's do a little bit of math. Here was a warm-up question. This function f of x equals x to the fourth minus 4x cubed plus 10. Where is this function increasing or decreasing? And then the second part of this is to figure out which critical numbers of f give local maxes or mins. So to talk about increasing or decreasing for f, I want to remind you, I know it was 2 weeks ago before spring break, but that means we need to just find out what's going on with f prime, because f prime positive is what tells us that f is increasing. Right, so if we need information about the derivative, let's go ahead and compute a derivative first. So here it is. Take the one term at a time. The derivative of x to the fourth is 4x to the third. After the minus sign, the derivative of 4x to the third is 12x squared. And then the derivative of this 10, well, that's 0, right? Derivative of a constant is 0. So that's why in this spot I'm pointing at right now, I didn't even write a plus 0. Okay, so to find out where f is increasing or decreasing, we need to make a sign chart for f prime. At least that's the easiest way, I think. So to make the sign chart, we need those partition numbers. We need to ask where is f prime undefined and where is f prime equal to 0. First of all, f prime undefined? Well, that never happens. F prime is never undefined, or you could phrase it, f prime is always defined, because if you look at f prime here, there's no concern of like dividing by 0. That's not going to occur. There's no fraction here. So then we just need to answer the other part of the question, when is f prime of x equal to 0? So let's set f prime, what we just computed for f prime up here, let's set that equal to 0. And then we'll solve this equation. So to solve this equation, a typical algebra student strategy is to do things to both sides. And you can do that, don't get me wrong. Sometimes that is more convenient, but as much as is possible, I want to remind you of the strategy we had started building before the break, which is as much as possible, you just want to factor. And I'll point out the reason why and remind you in a moment. So what can factor out of here? Out of both of these terms here. You can factor out a 4 and an x squared, so we'll factor out both of those, and then you have an x minus 3 in parentheses, still an equals 0. And then the point is from that, so I'm sorry I'm writing towards the right because I wanted to save most of the space on the slide for a lot of the pictures that we're going to draw. So out of this, what you get is x equals 0 or x equals 3. So I didn't show all of the algebra steps here just to save a little space on the slide, but I'll just point out, since we have multiplication equals 0, when you set this first part, when you set 4x cubed, when you set 4x squared equal to 0, then you'll eventually get x equals 0. When you set x minus 3 equals 0, that's where you'll add 3 to both sides and get x equals 3. So these two x values, 0 and 3, those are the partition numbers of f prime. Those are the only x values that we will draw in an f prime sign chart. So those x values of 0 and 3 are down there. Above, there's these zeros. Those are y values, or maybe I should right now call them f prime values. That is, when you plug in 0 in for x into f prime, you're going to get 0 out. Now, it's kind of nice enough to see this here, but because we didn't do anything to both sides, this is f prime, here's f prime again, this is f prime as well. Since we didn't do anything to both sides, we just factored. So this version of f prime is actually way more convenient. So say, like when you plug in x equals 3, you can plug that in over here to see that f prime's value is 0, but it's actually much easier to plug in x equals 3 here, because then you see that, 3 minus 3, right, this whole thing becomes 0. So that's what this 0 is about there. Okay, so this is the beginning of an f prime sign chart. Again, please notice it says f prime here and not f. But now what we need to do is we need to find out what happens in between, right? So we're going to test some numbers. We need to pick to find out what happens here and there and there, we need to pick an x value to the left of 0, some x value between 0 and 3, and an x value bigger than 3. And so you'll notice I picked probably the same numbers that most people were probably going to pick. You don't have to pick these specific numbers, but I picked x as -1 for this part over there, picked x as 1 for an x value between 0 and 3, and I picked x as 4 for an x value bigger than 3. And so you'll look, if I plugged in -1 for x, and I'm using this version of f prime, you'll notice I just copied the 4 first, -1, so x squared, so that's a -1 squared, and then plug in -1, so you have -1 minus 3. So over here you have 4 is positive, -1 squared is positive, and then -1 minus 3, I don't even want to compute the number. It's a positive times a positive times a negative. That's overall a negative or less than 0. So I'll give you a moment just to stare at f prime of 1, f prime of 4, see if you agree with the less than 0 and the greater than 0. If you don't agree, that's fine. Or if you have a question you want to ask, go ahead and unmute your mic and ask. So as I give you just a moment to stare at f prime of 1 and f prime of 4, I'll use that as an excuse to drink a cup of coffee until I hear a question. Okay, haven't heard any questions. So now that we have this negative, negative, positive for f prime, we can take this sign chart that we have and update it. Now, again, I would encourage you to take notes, and in the case of like an exam or quiz or something where maybe time is more crucial, you might just draw on top of this picture. But for your notes, it's much better if you redraw what you had up here, and then you add on this new information of this minus, minus, plus, which was taken from this less than 0, greater than 0. It's better to redraw. The purpose of redrawing is we did this, and then we had to think about this next, and then that's where we got this next. I think it's helpful for your notes to see that that process. Okay, so now that we have a sign chart for f prime, we can answer when is f increasing and when is f decreasing. Now here's where I need to recall some old things. I know this is now like ages ago, but f is increasing corresponds to when f prime is positive, and f is decreasing corresponds to when f prime is negative. So you see these two minus signs here. These two minus signs for f prime, that tells you when f is decreasing. So for this minus for f prime, that happens for x values to the left of 0, so that's what this interval is. And then this minus sign is for x values between 0 and 3. So f is decreasing on these two intervals, and we'll put a union sign in between. I answered the decreasing part first. The increasing part, when is f increasing? So that's when you have a plus sign for f prime. So f is increasing for x values bigger than 3. So there's this interval 3 to infinity there. So how are we doing going from the sign chart for f prime to this answering questions about f increasing or decreasing, which was part 1 of the warm-up? Do you have any questions? Okay, in terms of pacing, I hope we're also doing all right. And if not, you should please speak up. I will just maybe answer a question I anticipate that sometimes occurs, as people say, well, wait, if this function is decreasing for x values just to the left of 0 and just to the right of 0, why don't we just say that f is decreasing right at 0 as well? And I will be honest and say that this is an issue where on paper, like when people take quizzes or exams, I'm kind of okay with it. So I'm okay with people saying that f is decreasing on this interval, or excluding 0 or including 0. Either way is kind of sort of fine by me. It's sort of like f, but the book and probably WebWork questions are not. Like WebWork for this question would probably be expecting an answer that has these two intervals with the union symbol in between. So that's maybe why I'm mentioning this right now. Is the official word is that f is decreasing for x values to the left of 0, and then momentarily, just for a moment, when x equals 0, that's when f is not decreasing. And then right after x equals 0, so like when x is 0.1, then f is decreasing again. So that's the more full answer. Maybe don't stress about that all too much. But there is now the second part of the warm-up here, for which critical numbers does f have a local max or local min. So the critical numbers of f are these, we need these partition numbers of f prime. So this 0 and 3, we should see what's going on with those. So I put the question at the top of the next slide. I also drew the sign chart for f prime again that we just had. This will be super useful. Here's the first derivative test. This we had right before the exam. I really don't expect you to have remembered. It was a long time ago, and we haven't had much of a chance to apply it. So I've worded it a little differently here. So if you'd like to write it down, go for it. Or if you just screen capture or something later. So what happens with an x value c that's a critical number? That line didn't change, but what I did was I removed words and I put like a symbol here just because it takes up a little less space. So f prime, if f prime changes from a negative sign to a positive sign at that x value c, then f has a local minimum at c. If f prime changes in sign from a plus to a minus at c, then f has a local max at c. And if f prime doesn't change in sign at c, then f has neither a local min nor a local max at c. So the wording is a little different from what we saw before the break, in that I'm talking about the x values here now at c, and in the previous version of this we spoke more of the y values, but the general point is all still here. Okay. I think what I really want to say about this first derivative test is it's not worth memorizing this thing word for word. It's a lot easier to get what's happening if you remind yourself what the derivative means. So I'm going to draw a little picture actually for, like, say this middle point, just kind of over here. So if f prime changes from positive to a negative. So f prime positive, first of all, remember f prime is the slope of the tangent line. So positive tangent line, positive slope for the tangent line means you've got to have a shape that looks like this. You can't have a shape that looks like that, because here, if you drew a tangent line on this, those tangent lines have negative slopes all along here. So we can't have that, right? So let me erase that. You've got here, you have a picture where the tangent lines would all have positive slope. So f prime changes from positive, then it becomes 0 right at the top because of the critical number. So for a moment, there's like this flatness at the top, and then this minus sign there. So then the slope of the tangent lines have to be negative. So the general shape that has to be created has to be this peak, that starts like this, has this peak at the top, and like that. And that peak is why we have a local max. Right? So for me, I don't try to memorize this thing word for word because it's so easy to accidentally flip these two things. Right? This point here and this point there. It's easy to accidentally flip them. Don't want to do that. So that's why whenever I read this, or I just imagine that picture in my mind of positive slope, then 0 slope, then negative slope. That's got to create that peak that's right at the top of this mountain like that. Okay, so we spent a couple minutes here just trying to talk through at least one part of why this first derivative test seems reasonable, like why it's telling us the truth. And then now to apply it back to what we have over here. So take a look. We've got a change in sign. That's why I drew this f prime sign chart. We have a change in sign in f prime from a minus here to a plus. That happens right at 3. So the change from a minus to a plus means we have a local min at 3. What about at 0? You'll notice at 0, there's a minus and then a minus, right? So this minus, that minus. There's no change in sign. Doesn't change in sign. So that's why at 0, there's neither local min nor local max. And I know we already spoke a little bit about it, but I think that the first derivative test is easier to recall if you remember this thing that we noticed before the break, that f is increasing corresponds to f prime positive, and that f decreasing corresponds to f prime being negative. So information about the derivative, information about f prime tells you information about f. And of course, even this correspondence, it's easy to forget all this, but it's easiest to remember even these two correspondences here if you just remember that the derivative is slope of a tangent line. Remember that derivative is slope. It makes it much, much easier to remember that f increasing corresponds to f prime positive. Okay, oh, that was long-winded, and that was a lot of going through the warm-up, but I think it's helpful, especially after spring break. It would have been true after just a 1 week spring break, definitely true after 2 weeks. I'll pause for questions. All right, so what we're going to do, we're going to bring up one new concept today. And what we're going to really need, the ingredients we're going to need before will be quite a number of things. One thing is f prime is slope, right? Slope of tangent line, but a slope is a rate or a rate of change. So a derivative, you can view it as a slope or as a rate of change or both. And for what we're about to do, I want to take both ways of thinking of the derivative. The derivative is a slope, the derivative is a rate of change. We're going to apply both of these in just a moment. Now, just to summarize, here's what we had from the warm-up. We're going to use this in a question by the end of class again. In the warm-up, we took this function, x to the fourth minus 4x cubed plus 10. We saw that there was a local min at 3. We saw there was not a local min or local max when x equals 0. And we can actually draw a fairly decent picture. If we're going to draw, and there's these two x values that we already pointed out here of 3 and 0, then let's just compute what the actual y value is at these two x values. So f of 0, I just plugged in 0 for all the x's here, and you get 10 for the y value. And if you plug in this other x value that we got, this other critical number, into here, sorry I didn't show all of the arithmetic, I just wanted to spare you some details, but then the y value would be negative 17. So this helps you draw a picture. The point is, this is what the graph sort of looks like. This is not a perfectly accurate picture, but let's point out all of these features that we have. So first of all, there should be a point. So when x is 0, the y value is 10, so that's drawn in right here. Okay. And then when x is 3, the y value is negative 17. That point is drawn down there, right? 3 as the x value, y value is negative 17. Those things are in the picture. In addition, other things that are in the picture, we said that there should be a local min at x equals 3. So that was part of helped inform me that, okay, there's a local min right at that spot. And that, in fact, looks like a local min, right? So a local min is that valley. We use this language like that's a place where rainwater would collect. And then over here at 10, oh, sorry, not at 10, at would be the x value. At x equals 0, let me get rid of highlighting this point. Over here at this point where I drew the arrow, that's not a local min or a local max. So if rainwater fell onto that point, it would roll downward. If a balloon were released from below, it would not stay at that spot. So all of those features that we talked about over here, those are all present in the picture. And yet somehow the picture is good, but it's not perfectly accurate. So because of what we're going to do throughout the rest of this week, which is really about drawing functions, and because of what we're going to use this as an application for in a week or two, we need to use the ideas of calculus to help us draw more accurate versions of these functions. So the question that we're going to attack this week becomes, how do we make this picture more accurate? Well, to try to warm up to the idea of this, let me show you at the top of this slide, I've got two different functions. Both of these two different functions show you pictures of increasing functions, right? And then here at the bottom, there's two different functions, and both of those functions are decreasing. So as you move along the x-axis, the y value starts to decrease. Okay, that's fine, but like the two increasing functions, like this increasing and then this increasing function, they still look somehow different morally to me, right? There's something different about the shape. So like if we were live in class, what I'd have for you is this prop. I would take a deck of cards, and you know how people like shuffle a deck, or at least one of the ways is, you know, like you split the deck in half, and then you sort of, I'm doing this in my camera right now. I don't know if you can see this, but like you sort of bend the cards inward, and then so the cards are bent like kind of one way, and then once you've interlaced the cards, people kind of do a thing like this and kind of bend the cards the other direction, to allow the cards to like kind of fit together better. That's what I sort of see here. It's like it's like if you even just took a single poker card and you held it on the side and then you just squeeze the card, it might bend one way or the other. And that's kind of what I see here. I see an increasing function here, but the bend of the card is one way, and over here the bend of the card is the other way. Same down here in the two decreasing pictures, the bend of the card kind of goes like this. Sorry, now I drew too much, so it's hard to see. And then in this other decreasing picture, the bend of the card is the other direction. And that's the key thing that I want to try to address so that we can make our graphs look more accurate. Yeah, these graphs bend differently. That thing is called concavity. So here's the official definition. I don't think this is the thing you should write down. This is not the thing to focus on for the moment. We'll clean this up in a second, but f is concave up if f prime is increasing, and f is concave down if f prime is decreasing. So instead of remembering that, because I don't think that's easy to work with, what the heck does this really mean? Well, a moment ago, we reviewed something from before break, that f increasing corresponds to f prime positive and f decreasing corresponds to f prime negative. What I'd like to do is in this space over here, and I would encourage you to write this in your own notes right now, is let's talk about what happens if you take all of the f's that you see here and there and plug in an f prime. I know this sounds strange, but plug in an f for every f prime. So you have like, where there was an f increasing before, now we'll have f prime increasing. And what's that going to correspond to? Well, if you've got to plug in for f, you need to plug in an f prime, but there's already a prime here, then you're going to plug in f prime for the f, but there's already a prime, so you'll need to copy that additional prime, and you'll have f double prime is positive. Is that working for you? I hope I'm making sense. If I know it's a little strange, it's much easier to point live, certainly. Can I have you write the next one? So kind of in this space down here. Give you a moment. Let's make it active. I know I can't even see if you're doing this or not, but it's, I think, extra important to... All right, so I'll reveal. Here's what I have. So I have the box that says recall at the top. I have the box that says so. The point is, if we apply the thing we saw earlier in a new situation, so we're trying to say something about f prime, and this is helpful. Here's why. Because look, up at the definition where it said f prime increasing, that's right there. So what we're going to do is now piece this all together. All right. So the point is, this is, I think, the easier way to deal with concave up and concave down. So f concave up, that corresponds to f prime increasing. Where is that first correspondence coming from? It's from the definition. F concave up if f prime is increasing. But then the next correspondence, f prime increasing, that corresponds to f double prime positive. That's what we just said over here. Let's see if you can now track for yourself. Same deal. F concave down corresponds to f prime decreasing. F prime decreasing corresponds to f double prime negative. How are we doing? And pause. Wait for a question. All right. So look, I think the real point that I want to make here is to say that instead of using the original definition at the top, it's a lot easier to think about concave up and concave down if you instead remember that f concave up, we should point, f concave up corresponds to f double prime positive. So now, okay, in the warm-up, f prime positive said something about f. Now f double prime positive also says something about f. So f double prime positive says that f is concave up. F double prime negative says f is concave down. So before we dig into an example, I want to show you pictures of what this looks like. So this right here, what's in the green box, basically gives you a very quick and dirty way of computing when f is concave up and concave down. But before we do that, we need to talk about what the heck does this mean? What does this look like? So that's where the definition is important just for a moment. So don't stress about this too much. But please remember, we just said earlier that the derivative is slope, and slope is rate of change. So when you see f prime prime, one of the primes could stand for slope, and the other could stand for rate of change. So f prime prime, read one of the primes as slope, one is change. So then we can talk about the change in the slope. So take a look at this picture here. I've got this sort of smile shape. And the point is, if you, sorry if the function I drew in kind of rather thin, because I wanted to emphasize the tangent lines that I was going to draw on. So I drew thicker tangent lines in blue. And you'll see, for instance, this tangent line, slope is like something negative, and then, I don't know, eyeball it. Maybe the slope here is like -5. I don't know. And then the next tangent line, slope is negative, but not as bad, right? So maybe slope is like -2, something like that. Then over here, it looks like the slope of the tangent line is 0. So f prime is 0. And then f prime, the slope of the tangent line is like, I don't know, maybe 1, right? And then over here, maybe the slope of the tangent line is 8. I don't know, whatever, right? So the point is, if you look at the slopes of these tangent lines, how do they change? The slopes keep getting bigger and bigger. Right, the slopes are increasing. That then by definition is concave up. So I've spelled concave. I've typed it a little incorrectly, but that's a picture of concave up. We'll abbreviate that CU. And if you look at this other picture, you have a positive slope. Maybe that slope is like, I don't know, just eyeball it. Maybe it's a 4. And then over here, maybe the slope is a 2 and the slope is 0. And the slope is like a -1 maybe. And the slope is like a -5. So over here in the second picture, the change in the slope, the change is actually, the slope is getting smaller and smaller, and that by definition is what concave down is. So I think the easy way then to recall is that the shape of f is, for concave up, it's like a cup. And so up rhymes with cup. Concave down rhymes with frown, right? That's at least to make it kind of easier to remember. Frown looks like that shape. This is where I normally throw in my terrible Frozen joke of saying, okay, bye. And now I can't even see people rolling their eyes at... Okay, anyway, so look, the whole point is the last slide was, how do we compute it? How do we detect it? And this slide is, now that we can compute it, what the heck does it look like? And so we want both of those ideas together. Sorry, that was a lot of information. Let's summarize it and then look at examples. So earlier, these are the same 4 functions I showed you pictures of earlier. I just earlier said that this upper left one and then this one in the upper right, these are both pictures of increasing, because they are, but they bend differently. And this bend is like part of that cup. So this concave up. This is an increasing function over here, but the bend is not like a cup. It's like half of that frown. So this is concave down. That's why the CD is there. Same thing down here, right? There's these 2 decreasing functions, and this one's shaped like half of the cup, so this is concave up, and this one's shaped like half of the frown, so this is concave down. So these 4 shapes help us get a more accurate version of what a function looks like. The second derivative basically is going to help us determine more accurately what the graph of a function is. Okay, enough talk, enough what this looks like, and we need to make this more concrete, so let's look at an example. The example I want, because it's going to help us out a little later, is the same function as earlier. This is the function from the warm-up, x to the 4th minus 4x to the 3rd plus 10. I want to know when is this function concave up, when is this function concave down. So we need to just know when is the second derivative positive versus negative. So we already had the first derivative. So if we need to know when f double prime is positive or negative, it helps us to just find where f double prime is 0. So what we're really doing is building a sign chart for f double prime. We already computed f prime. Not that we need f prime so much. We just need f prime from earlier to get f double prime. So take the derivative of 4x cubed, you get a 12x squared. Take the derivative of this 12x squared term, and you get a 24x. F double prime isn't undefined ever. There's no dividing by 0 problem or anything like that. So we'll find out when is f double prime equal to 0 first. So if we set this equal to 0, usual story, let's try to avoid doing things to both sides if possible. I would just prefer to factor. You notice that you can factor out a 12. You can factor out an x. So we'll factor out both. End up with 12x times x minus 2 equals 0. And then when you set the 12x equal to 0, you get x equals 0. When you set the x minus 2 equal to 0, you get x is equal to 2. So it's these two x values, the 0 and the 2. Those are the only two x values that we should include on a sign chart for f double prime. So down below the sign chart where there's a 0, there's this 2. Those are the special like cut locations in the sign chart for f double prime. The zeros that are written above, these are the f double prime values. So when you plug in 0 into here, or here's another way of writing f double prime, this factored version, because we didn't do anything to both sides. If you plug in 0 for x, you're going to get a 0. And then if you plug in 2 for x here, you'll get a 0 again. And same story as with the f prime sign chart. For this f double prime sign chart, we want to now go and ask, wait, what happens? So we know f double prime is 0 here, f double prime is 0 there, but what happens in between? So we want to know, like, we should pick an x value between 0 and 2. There's an obvious one that everyone's probably going to pick, right? You're going to pick x equals 1. This is actually a good time to just point out a common error people make. Sometimes when people pick x equals 1, what they'll do to do so is they'll, right halfway in between, do that tick mark and draw 1 there. I would please ask you to avoid doing this. I think if you do this, what I've seen happen is people will, because they draw in this extra, like, tick mark, this extra cutting of the number line, then people start like noticing or thinking that they need to pick another x value like 1.5 where I just drew the arrow. It just gets messier and messier every time you pick a new x value to draw an x value there. So I encourage you to be lazy, and the way to be lazy here is to not draw in 1. Okay, what do you do with the 1? You just compute what's going on with f prime, or sorry, with f double prime, and just do that below. So so down here, I picked x is -1, x is 1, x is 3. I'm not drawing on top of this picture. And if you plug in, I'll just pause for a moment. See if you plug into f double prime, which is here, I rewrote it over there. Does this work for everybody? F double prime of -1 is bigger than 0. F double prime of 1 is less than 0. F double prime of 3 is bigger than 0. Again, this is not about computing specifically the numbers, right? I'm not sitting here going, what is 12 times -1 times -1 minus 2? I'm saying it's positive times a negative times a negative. So that's got to be positive. And pause for questions. Okay, now that we have the info that we do, I will include this information in the f double prime sign chart. So this plus minus plus is here, here, here. So now that we have a sign chart for f double prime, we can say something about f. So the first part of the question here was, when is f concave up? That's when you get these plus signs for f double prime. So so this plus sign occurs for x values to the left of 0, so that's this interval, and then this plus sign occurs again, a plus sign for f double prime, when x is bigger than 2, so that's this interval here. So this sign chart for f double prime tells us something about f. Now, this is correct as written. This is not a typo. And this is super important. This says f is concave up on, right? It's not, it would be, I'm going to make a mistake right now. If I drew 2 prime signs right there, then what I've written is an error. It's not f prime is concave up on. It's f is concave up on. I think that's the most important thing. If we really want to get a handle of what's going on with the calculus, information about f double prime tells you something about f, right? F double prime positive tells you that f double prime positive tells you that f is concave up. So same deal. This minus sign that's over here for f double prime tells you information about f. It says that for x values between 0 and 2, that's that interval right there, f is concave down. So we're done with this question, which is why the happy face is there. But the more important thing to do now is say, okay, we've got this information. What do we do with it? We can draw a more accurate picture. So here's what I'd like to do is we're going to take this f double prime sign chart. And here's the new question. Same function, x to the fourth minus 4x cubed plus 10. But now I'd like to use this concavity information from f double prime together with the information from f prime that we had from the warm-up to make a better picture. So in the warm-up, way back at the beginning of class, we had the sign chart. And I would encourage you to draw it. And then underneath, I'm going to draw the f double prime sign chart. Now, the key thing I want you to point out, maybe just before you draw, I'll give you time. The key thing to point out is you see this x0, x is 0, those are aligned vertically, but you see this x is 3 over here, and 3 would be, x equals 3 would be over here, which is why the 2 is drawn a little to the left. I think that's the key thing. I'm going to give you a moment to draw this, to draw these f prime and f double prime sign charts, but it's helpful to make sure that the x equals 2 is a little to the left of the x equals 3. All right. So now we have information from f prime, we have information from f double prime. Let's say something about f. So here we've got 3 charts going on, one for f prime, one for f double prime, and one for f. The easiest part of this one is to look to the left of this 0 here. So the minus sign for f prime, I want you to recall from before break that means a minus for f prime means that f is decreasing. So I couldn't write out the entire word decreasing because of what happens later. So the plus sign, this is the new thing. The plus sign for f double prime, it corresponds to f being concave up, abbreviation CU. Okay, this is going to get a little tedious, and I'm sorry about that, but I just all throughout this week, we're just going to keep practicing these ideas and just get more and more used to it. Then take a look at the next part. So you'll notice there's a 2 and a 3 down here. Some people find what I'm about to do helpful. Some people find it not helpful, but I'm going to try it and then I'm going to erase it. I'm going to lightly draw in just sort of like a dotted line. And this is, I'm so sorry to do this. So I did that where the 2 is. I do that where the 3 is. And this looks overall very messy, and I'm sorry about that. But now the point is, where did the decreasing in the CD come from? Well, between x is 0 and 2, you'll notice f prime, this minus sign applies. In fact, this minus sign, if I just get rid of the dots for a second, the minus sign applies for all x values between 0 and 3. So definitely the minus sign that's here that I'm pointing at applies, and that's why f is decreasing. And then this minus sign, the minus sign for the f double prime, that applies, that's where the CD comes from for f. In the next part, this is where things get a little tricky to look at. Where did the decreasing come from? Well, that came from this minus sign. And I know this minus sign looks like, wait, is that the one that applies? Is it this plus sign? It really is this minus sign, right? I mean, again, let me kind of get rid of the dots for a second. And between 2 and 3, f prime, it's this minus sign that applies. This minus sign applies all throughout this part, and so it applies over here. And even with these dots so that's why I think it's helpful to draw these sort of lightly. But this minus sign over here is what applied and why we have this decreasing written right there. Then finally, this plus sign that's over here, that's a plus sign for f double prime. That's why there's a CU here. And again, with the dots in the way, maybe it's a little harder to see that, but you know, with the dots out of the way, maybe it's just the dots help in sort of drawing these 2 and 3 in exactly the right spots where they should be. That's, I mean, this is really tricky to put this all together. So the point is, yeah, maybe without the dots I'll do this. This minus sign for f prime is a decreasing for f here, and then this plus sign applies for x values bigger than 2. For f double prime is the CU for f. And then finally, for x values bigger than 3, this plus sign is finally what applies. This plus sign from f, this plus sign from f prime says f is increasing. This plus sign from f double prime says f is concave up. So maybe I'll put the dots sort of back, and maybe I'll pause and say, who's got a question? Because this looks a little funky at first. Doing okay overall? Okay. Well, you know, it's kind of up to you whether you like drawing in that lightly dotted line or not. But now let's take a look at the shapes we're going to get. So we've got this decreasing concave up looks like this, and decreasing in concave down looks like that. Decreasing concave up, actually that's the same shape we just talked about over here. And then here's a new one. Increasing while concave up, increasing while looking like a cup, looks like that. So in these specific, for these 4 regions or areas, that's what the graph of the function is going to now look like. And I went ahead and just plugged in 0, 2, and 3 into the original function f over here. Now you already saw the 10 and the negative 17. Earlier during the warm-up, we never dealt with x is equal to 2. So I just went ahead and plugged in 2. I spared you the arithmetic right now, but you're going to get the y value equal to negative 6. The point is, with this information, we can draw a much more accurate picture. So I'm going to just try to do that over here. So when x is 0, we get a y value 10. So there's like a point there. Maybe I'll just write 0, 10 for that point. When there's 1, there's 2. So when x is 2, we get a y value of negative 6. So there's this point here. 2, negative 6. And then when x is 3, we get the y value is negative 17. So this is certainly not to scale. It gets the point across. Okay, so then we get that point there. So this is my, 3, negative 17. And then the point is, so we've got these 3 points, this one right on the y-axis, this point 2, negative 6, and this point 3, negative 17. And now think of these 4 things as like Lego pieces. We just need to snap the pieces together. So when x is to the left of 0, the Lego piece should look like that. So we've got a piece in the graph that should look, roughly speaking like that. And then when x is between 0 and 2, the Lego piece should look like this. So think of it like there's a connection point on this Lego piece right here that should snap and connect to that part right there. So that should look like that, roughly speaking, And see if then you can connect the next Lego piece, right? So this Lego piece that I just circled, that part of the previous Lego piece should connect to this part of the next Lego piece. So maybe take a moment to try that, to draw in what happens between 2 and 3, draw a Lego piece that looks like this. And then after 3, after you get to this point, draw in a piece that looks like that. So overall, I hope you tried it instead of just watching me. It's, I think, more important than ever before that you do something a little active because we have a little less interaction now. Overall, this is what the picture ought to look like. And if you clicked on this link, let me see if this will work. Last section, it did cause a little bit of issue. So let me see if that's going to load. Come on, Desmos, do your thing. I'll wait for it just for a moment. Oh, here we go. Here we go. Come on. All right, I'm gonna let that go because we only have a couple minutes. But if you clicked on the link, you'll actually get a fairly accurate version of that picture. Here I have it just built in the slides as well, so I just drew it using Graphing Calculator and then took a screenshot. And so that looks actually very accurate to what we just did. The last little thing I want to say is that there's this concept called an inflection point. And an inflection point is when you have a change between concave up and concave down, or between concave down and concave up. So I'm sorry this says answer. This is rather more an example. I would like to point out an example of this based on the work that we had earlier. So earlier for F, we had said, well, right at 0, you have a change, concave up to concave down. So that's where you have an inflection point at this x value 0. Then concave down to concave up, there's again a change that happens at x equals 2. So there's another inflection point. You have concave up, then concave up. There's no change there. It's concave up and concave up. So with no change, there's no inflection at 3. The inflections here happen when x equals 0 and when x equals 2. The important thing I would like to point out in the definition, though, for an inflection point is that an inflection point is a point. So because we have a point in the graph, we should write them as points. So this is a point. I mean, the x value is 0 here where there was a change in concavity. There was a change in concavity here. There was a change in concavity at this x value. Those x values are written right there, 0 and 2. But because we needed a point, I just took the y values that we got earlier. So that was when we plugged directly into f. When we plugged into f here, the y values were 10, and the y values was -6. So these 2 points are the inflection points. These are the places where there's a change in concavity. Questions on that? Let me see if, oh, okay, finally, sorry to change the order on this. Since I do have a minute, I'm just gonna, now that I was curious if Desmos did load, what I did was, first of all, in red, you can try this on your own later too, because you can download the slides and click on the link, but I'll just, since I've got a minute, I asked Desmos to just give me the part before 0, then just the part between 0 and 2, just the part between 2 and 3, and finally the part that's after 3. And you'll see those individual Lego pieces snapping together here. And then I also just had Desmos, I said, just give me the whole thing. So now the whole thing is shown in green there. I guess the point is it takes a little getting used to piece together all of these pieces. And tomorrow we'll practice this more. We'll talk about what concavity grants us. Like here today was just like, what is concavity? What does it look like? How do we compute it? And then tomorrow we'll spend a little more time talking about like, what can you do with it? Before going though, I just quickly, in case people did join late, and I think it's just helpful right now in terms of announcements, I just want to remind you, I'm here for you. I know that we did still spend a lot of time doing math, but if you've got something that's coming up, just please let me know. If you have questions, see me in office hours, or email me and say I want to meet at a different time for office hours. Meet by phone. Try the practice quiz, and there is an actual online quiz for tomorrow as well. So that's what I have, and otherwise I'll see you tomorrow. I'll take questions if anybody has them. Otherwise.